Eugene Mayer Professor of Statistics and Political Science. And so I'm going to do small n, small p now. So I miss my friend. He is also in Hawaii conference. He's from Yale, and I miss both people. From Yale. So there must be something going on at Yale. I don't know, sample size equal to 3, so we can make an inference. But anyway, just going to talk about Debiasing random forest for treatment effect evaluation. Just the floor is yours.
Thanks. Thanks for the introduction. I apologize for not being there. I was in Berkeley as of this last weekend. Because of COVID churn, my daughter's school production got moved to this week, and I had to be here to support her, so I apologize. But she's 11, she wouldn't understand. But I very much wanted to come, and I thought until very recently I'd be there. So I apologize to everyone, and Peter in particular. So today I'm going to talk about this project that grew out of a project that we did with Peter, and this is joint work co-authored with Ben Yu and Theo, who is a graduate student of ours. So a couple of years ago, we got Peter to write on causal inference. And by we, I mean Ben and another graduate student of ours, Soren Causal. And this paper is on estimating heterogeneous treatment effects. What these are is, as the data has grown very large, as we get big N and big P, policymakers, whether it's in medicine or political campaigns or it's on online platforms, so on and so forth, they're not interested so much anymore on what the treatment effect is on average. They want to know what the treatment effect is for various subgroups so they can target the treatment to those subgroups. So that's the heterogeneous treatment effect problem. I'm going to give a little more formalism in a bit. It's a difficult problem. Even though the data has grown large, the estimation problem is quite difficult. To my knowledge, that's the only causal inference paper Peter has written, but Peter's had a very large effect on the causal inference community, which is the causal inference community has grown over time. And Simons has this spring several workshops on it. And one of the core workhorse theoretical models in the causal inference literature is semi-parametric theory and the semi-parametric efficiency bound. And Peter, with various co-authors, and it's just one citation of many of Peter's work on this, has developed that theory. And for reasons we'll see in a few slides, in the case of the average treatment effect at least, the theory has a naturalness of application in causal inference. Sociologically, not just by his written work, in a very personal way, Peter's had a large effect on the causal inference community by the people he's trained. Whitney Newey, who's a very prominent econometrician at MIT, was a visiting scholar in Berkeley in '86. He took Peter's class, which Peter covers semi-parametric theory in, and then he wrote some papers and then trained a lot of students. He then mentored Jamie Robbins. The way Jamie tells it, Whitney was trying to convert him to become a Mormon during this process. The conversion didn't work, but he was taught semi-parametric theory. And then Jamie has developed it for causal inference and trained many students as well. So in a very personal way, Peter's had a large impact. I remember talking about this with Peter, and Peter looked vaguely bemused and said, well, was the theory of any use? Was it interesting? And so a lot of this talk is going to be, Peter and I talked a lot about how theoretical statistics interacts with applied statistics and actual applications. And also Peter has an interest in politics and political campaigns. And this talk's going to feature on both of those topics. So what's the treatment effect estimation problem? So this problem and its policy implementation version is what's led to this work, which is developed out of the work with Peter. Out of the work with Peter, the technology we had and the methods we developed are now in online platforms, part of tech pipelines in a lot of major firms. A lot of other people are using them, and I keep getting email about it. And most of the problems that people face are this policy planning problem. So you estimate a treatment effect, right? Which is the effect of a drug, what's an effect of an online ad, what's an effect of a policy to get people to turn out to vote. And then For the policymaker, this becomes a cost-benefit thing. There's many, many things they could spend their dollars on, many, many things they could do to get people to turn out to vote. There's many, many things they could do to get people to buy a certain product. And there's a variety of drugs or medical procedures one could do. And now you have to trade off costs and benefits, right? So there's many, many applications. And the healthcare costs, in case, it's often, not monetary costs. It's often just, different drugs at different pluses and minuses. In some cases, it literally is monetary costs. For years, I used to do work with NICE, the National Center for Clinical Excellence in the United Kingdom, which would literally value a quality adjusted life year to be about 30 to 50,000 British pounds. Interventions that give you a greater return than that, they would like to fund. Interventions that give you a lower return than that, they would not like to fund. So when you estimate these treatment effects, you need it to be scaled properly, because on the other side is going to come costs, and you got to weight them off, right? The thing is, any bias now in your estimates of your treatment effects is going to be really bad, right? Because you can imagine other cases where all I got to do is just rank order of what I think the treatment effects are, and I'm going to take the top 5. At which point then bias, as long as I've maintained the correct ranks, the bias isn't going to be a big problem. But in the cases I'm interested in and what motivated this work, no, the bias is actually pretty fatal. The motivating example and the data examples I'm going to give here are going to be election campaign, although I have finance examples, there's medical examples, there's online tech firms that face this using the methods we developed and others, right? In the election campaigns, you have finite resources, you got to allocate them over various policy interventions, and you want to and you might want to do various things, might want to just increase turnout, you might want to win an election, you might want to do something else. We're going to get into that. Now, it turns out that in this world of heterogeneous treatment effects, we're not just estimating the effect on average, but for subgroups, even when you have randomized experiments, with large-scale randomized experiments, obtaining valid confidence intervals has been quite challenging. Even in cases where the estimators themselves have asymptotic normality results and so on and so forth, the coverage has been quite bad. So one move is conformal intervals. There's a very nice paper by Liwa and Emmanuel on using conformal intervals. With the bias adjustment, we can get decent coverage as well, although under clearly stronger assumptions than conformal intervals, but the interval length is much, much smaller. The interval length of conformal intervals is so large in ways I'll show that I think it's going to be pretty challenging for applied people to use, in a sense that you can have an experiment where the average treatment effect, for example, is a t-statistic of 3, so it's very well powered. It's a randomized experiment, so it's a believable confidence interval. And when you do conformal through your heterogeneous treatment effect estimator, it will cover 0 for every subgroup. At which point, applied people do what they do, and they'll say, well, I'm not going to believe that. Someone tells me there's an asymptotic normality result for this other thing. I'm just going to use that. But I'll emphasize the key thing motivating is not the confidence intervals, although present results because they're easier to digest. It's the policy making things, which is to say that confidence intervals are rarely our first order problem when you actually have policy making issues, right? One can see this. I'll give you an example of, say, from COVID. We did large scale mRNA randomized trials at great and massive social cost because we delayed the implementation of the mRNA vaccines. And every month you delay is trillions of dollars to the global economy, many lives. And we got p-values that are credible and design-based. But the minute the randomized trial landed, all the policy questions came from, well, the antibody response is declining over time, the virus is mutated, should you do a booster? And there was a debate on that. The Israelis had one view, the FDA had another view, the Biden administration leaned on the FDA to follow the Israeli view. The issues here were not really confidence intervals. The issues were all about what the social welfare trade-offs were. And so it's just to highlight the thing that we actually care about most of the time here is very little to do with the p-value we get, although the p-value is something we can, guarantee, at least in sample at the time. 3 months later, that might not be a meaningful thing, as it wasn't for the mRNA vaccines. If you ask me now, by the way, what's the probability? What is the causal effect of the mRNA vaccine for you not to get infected? Nobody knows. Nobody knows. It's not a pinned down estimate, even though we spent trillions of dollars on opportunity costs doing those trials, which I'm saying we should have done, but just to highlight what little we know from those trials in practice. All right. So in these election campaigns, there's various trade-offs to be had, right? So there's three general categories of people and policy trade-offs. They're all going to involve different trade-offs on, like, say, bias versus variance and other things. You can have a nonpartisan group that just wants to increase turnout, right? So this is a very easy thing. For this kind of group, if you just ranked ordered who you should apply treatment to, they'll just take it, right? But then you have two other types, which is you can have a major donor who doesn't care about an individual election, but just wants to, say, flip the Senate or flip the House. So this donor doesn't care if you increase someone's vote percentage from 60% to 70%. This donor really wants to move elections that would be 49% to 51%, because she's interested in the overall portfolio, not an individual race, and wants to, like, do that under the face of a budget constraint. So now bias is a pretty serious problem for this person. And then the most common case is a candidate just aims to win, but candidates run scared. They don't want to get 51%. They want to just maximize their vote percentage, but they care who is going to be turned out. They're not going to pay to get the opposing parties people to turn out. All right. So sorry, I keep going the wrong way. So just some notation here. So this is under the Neyman Rubin model. For those who know it, you don't really need to know it for the purpose of this talk. You have individual treatment effects. So Y sub I1 is the outcome of individual I under treatment. Y sub I0 is the outcome of individual I under control. And you have D sub I, which is the treatment effect of that individual. Now, the key problem is, going back to Neyman 23, you only observe one of these two, because either I encourage someone to get out the vote, or I don't. I give someone a vaccine, or I don't. So this D sub I is a theoretical quantity that I don't directly observe, right? So when there's an estimator D sub I, just denote that tau hat sub I, but I'm never going to directly observe that. So back when data was small and we didn't have that many covariates, everyone was pretty happy because it's about the only thing you could estimate. It was the average treatment effect, which is the difference of these two, the mean difference between these two. And because the linearity of the expectations operator, this just becomes an easy problem, right? And this is also then calls for why semi-parametric theory was a pretty natural fit for causal inference in this case, in the sense of, well, this part is parametric, right? Because the linearity expectations operator. But in case where you don't have a randomized experiment, or if you do and you're worried about the finite sample properties, you're going to get a nuisance parameter, which is going to be in general non-parametric, which is going to be the covariates that have a relationship with your treatment assignment and also the outcome. And if it's not randomized, you need to control for them in order to not get bias. Even if it's randomized, you wish to control for them to reduce your variance. So that's the naturalness of the semi-parametric theory in the usual case. Now it's not so natural, because now what we're interested in is this conditional average treatment effect, which says, oh, I want to know not what the average treatment effect is overall, but I know what the average treatment effect is for substrata of X, right? Conditioning on X, the way I've written it, you know, if you had enough data and your parameters were small enough, P was small enough, you could just like chop it up into subgroups. And that's exactly the after you get a heterogeneous treatment effect estimate that you claim using complicated things, in which we'll get to, the way you would validate it is exactly do a standard randomized trial for that substrata of X and see if you could actually match it. But in general, this function here is not so easy to estimate. You know, you need smoothness and whatnot, and it gets quite tricky, right? So in our paper with Peter, what we did is we'll say, all right, we want to estimate this conditional average treatment effect. There's many ways you could estimate it. You could use a neural net, you could use random forests, you could use OLS, you could do many, many things. There's many different things people have. Well, let's create meta learners. These things that your individual learner can be a random forest, it could be a Bayesian regression tree, it could be linear regression. It's gonna take those and it's gonna target this conditional average treatment effect. So you're gonna break this down to sub-regression problems, right? And it's gonna use some other estimator to solve the sub-regression problems. It's gonna use those base learners. The thing that this talk and the thing that this evolved to is, well, those base learners themselves are gonna have some bias. Random forest is very commonly used here, and it's gonna have some bias. And if you don't fix that bias, you get this very serious issue in policy planning and also then in confidence interval estimation. If you were worried about that, right? So the reason this thing breaks it up easily is, again, because the linearity of the expectations operator. It's like, all right, we want to estimate this, which is your treatment effect initial and X. I can break this out into two regression problems. I want to know what's going to happen to your outcomes under treated given X and your outcomes under control given X, which then leads to the most simple meta learner, which is the oldest thing in the literature, goes back to at least the 1950s, one imagines earlier, which is say, I'm going to split the data into two, control and treatment groups, and I'm going to estimate separate response functions for both, whatever learner you wish, right? I'm going to estimate mu1, your learner on the treated, W denoting treated, mu0, your learner under control, and then you just predict through both to get your estimate of the conditional average treatment effect at X. The obvious thing to note about this is, yes, you can do this, but if the underlying functions are hard to estimate, as they currently are, since we have a big P, right? If the expectation of, say, your outcomes under control given X is very rough, lots of parameters in it, is hard to estimate, but your conditional average treatment effect, the difference between the two is very easy to estimate. You've gotten yourself into a hard problem. And it's often the difference, the conditional average treatment effect itself is much easier to estimate than the base regression problems, because as I wrote one paper, did some theory from data from one large tech platform over thousands of their experiments, the modal treatment effect is 0. Most treatments we do have no effect. It's just a 0, which is a constant treatment effect. So the CATE has a simplification that the underlying regression functions don't, and this thing is not exploiting that. So it's not going to have a good minimax rate. Another thing you can do, and these are the only two I'm going to talk about in this talk, and I'm going to talk about the one that Peter and us proposed because it's not really germane and core to what I want to get across here, is the S learner, which is just, I'm going to run a single model, is I'm going to just treat treatment like any other covariate. I'm just going to treat it like any other covariate. I'm going to run my regression model, however that is. Could be a lasso, it could be neural net, it could be random forest, do whatever you wish. And then at the end, I'm just going to predict through setting treatment to 1 or 0. Now, when your treatment effect is 0, this may be a better idea than this T learner because it's not going to spend its time splitting on the treatment indicator when that wasn't great. This still is not going to necessarily be a fantastic idea because, again, it's going to be sitting there estimating this very difficult to estimate response function if this were to be difficult to estimate. But these are two base learners. The problems I'm going to talk about occur with this X learner that we worked on, which is in the case of one of your groups, usually control is way, way larger than the other, which is what happens with online experiments. There's also doubly robust estimators, and they all have the same problem with this bias because the bias is coming from the base learner, right? So the most common, a very common used base learner is random forests. And we have theory, we have results of asymptotic normality from Vogger and Athey and some previous work. I'll talk about that in a little bit. And then people can go off and create confidence intervals. Those intervals just have very bad coverage in finite samples. And by finite samples, I mean, you have hundreds of thousands of observations. And P could be like 100, and they have terrible coverage. Even when you have millions of observations, if P is 100, they sometimes don't have the greatest coverage, but it gets better. But as a prediction algorithm, it shows very good performance in the regression case, particularly when signal to noise is not very good. You can trust applied people to use it pretty well because there's not that many hyperparameters to tune, and it handles sparsity and everything pretty well. One of the issues is Bryman himself knew that one of the key tricks for the random forest thing, for it to work quite well in prediction problems, is he's introduced some bias. And he introduced bias by subsampling the splitting features, the M-try thing in the algorithm, right? Because you're bagging the trees, and then you're also at every point, you're subselecting the covariates you have, right? And that's going to decorrelate the trees across bags. That's what's giving the advantage of bagging. If I keep finding each tree in each bag, I'm not going to gain anything from bagging. I need to introduce some randomness across bags, but I'm also going to introduce some bias because I'm not allowing at every split point for me to examine all the covariates. And you can imagine, say I have 100 covariates, only 5 of them matter. but those 5 are only going to show up sometimes, and I'm going to induce this bias that occurs. Breiman knew about this. He wrote about it. He even tried to do a bias adjustment that mostly has been forgotten in the literature. It's very easy to show. It's trivial to show that random forests have this bias in this simple case. There's 10 covariates. It's linear model. It's deemed to be true. And only 3 of them matter. You fit a random forest. The truth is on the 45-degree line. You get this biased estimate. And it's very straightforward to show. Our very simple theory that I'll talk about at the end, it deals with this simple case, this linear case, right? So that's the bias you want to get rid of. It's the literature kind of forgot about it, but Breiman knew about it. He tried to have a fix about it. His fix had his own issues. Right. So there's previous work in trying to fix this bias. Breiman's work itself, I think, could best be understood. I think Peter was not alone. Other people told me as well that Leo had thought that random forests can't overfit. Someone else told me at one time people thought AdaBoost couldn't overfit either. I guess that's always the way it works. Random forests more certainly can overfit, and his attempt at bias adjustment turns into a boosting thing that you run random forest, and then you keep running it over and over again on the residuals. Using all the covariates, and you stop at some point using a holdout set. Its performance can get it. Now you get this problem of you can very easily overfit. You make predictions outside the range of Y because of the boosting component, and now you're kind of in the soup of I got hyperparameters. Once I have hyperparameters, why am I not just doing XGBoost? Why am I not doing neural nets? Because those are now once I bit the bullet and say that I have these hyperparameters I have to tune carefully, then why don't I just use machinery and estimators that are built around that? There's been other attempts as well. None of them quite work well without hyperparameter tuning, which is what you're trying to avoid in these pipelines. Because if you're trying to avoid them, I'm not going to do random forest. I'm going to switch to XGBoost or something else that's a little more complicated. That does very well in these prediction problems. If you go to Kaggle, random forest gets beat by XGBoost quite handily, although random forest is quite competitive. So I'll tell you our algorithm. I'm going to give you some simulations, I'm going to give you a data example. I'm going to show you some very simple theory. And our algorithm is very simple, and it's simple consciously because you need something that you could deploy in pipelines that will have some semblance of do no harm. Right? So it's not like you have to make sure that the analyst is getting very cute about hyperparameters, because I'll guarantee you the analyst will not get cute about hyperparameters, because that's just not what happens in practice, right? So what we do is we just run the forest, and then we just regress Y on the predictions of the forest. You don't let the forest see its own covariates again, and there's not boosting. You just run Y and Y hat again using the forest. Right? And at the last step, you do a regression adjustment with just 2 covariates, which is the intercept and Y hat. That last thing at the end ends up being important. If you don't do the OLS thing at the end, the forest can continuously regularize, actually. It could be that as I go through these rounds, the regularization problem gets worse, not better. The other thing we do, and I'm just going to parenthetically highlight this, is that theory for random forest is very hard to do. So what people did is, in order to get the asymptotic normality results, they kind of like worked very hard to ignore that you run a random forest. And one way to do it is you could have done what Leo did and just do like out of bag, which just made a lot of sense. But what they did instead is did this honest random forest. And what the honest random forest is I subsample my data. Now, whether it's by bootstrap or I take a half sample, doesn't matter. And then what I do is I split my data again in half. Now, it doesn't have to be half, it could be some other proportion, but it doesn't matter. And on the first half of the data, I grow my forest using the usual rules. Then I delete all my outcome data. And then from the other half of the data, I drop it through my tree, and that's feed into my terminal nodes, and that's my outcome data. And in this way, I've made my tree structure conditionally independent of my outcome. And now I can, like, for the purpose of theory, mostly ignore that I've done random forests, right? And I just got some boxes. I independently got the boxes, and now I'm off to the races under regularity assumptions to go prove asymptotic normality. That's the way the theory works. It's great. And the theory relies on subsampling, which is also great, which is Peter's done work on. And the reason it needs subsampling is because when I split my data into the splitting set and the averaging set, and then I'm going to predict through, I got to make sure that when I'm predicting through, the observation I'm predicting through isn't sitting there in my averaging set. Because if it is, I got a problem again. I break the independence. So the theory gets around it by subsampling. All of the software that uses this just sets the sampling rate at 0.5 as a ratio. I know what 0.5 is. It ain't subsampling. It doesn't say square root of n because no user would ever use that because it gives terrible performance. So here's a classic case. The theory is correct. The theory does what it does, and it ends up in an algorithm that by its very default design by the same authors will violate the theory. So you don't actually, so what you end up getting is, unlike if you just roll back to Leo's original code, it wouldn't have this problem. This other code has the following problem. I randomly generate y, univariate normal. I randomly generate x, univariate normal. I regress y on x using the forest and go, what's the correlation between y hat and y? It's going to claim a correlation of over 2, over 20%. Why? Because it's not subsampling like the theory required. This definition of honesty had that y sitting in the averaging set, and you got yourself a problem. So instead of relying on subsampling, we changed the algorithm, more inspired by what Leo would, I think, do, but still get this honesty principle by just doing an out-of-bag kind of honesty. I won't get into it, but you're just guaranteeing by algorithmic design that when I'm predicting observation I, it cannot be sitting in either the data set that constructed the tree nor the data set that I got the averaging data from. All right, and this is an example that we write theories one way, it looks fine. And then 3 steps on, you're like, well, what are you going to actually do in the code? You're actually not going to do subsampling for this problem because the performance as a predictor would be quite bad, even though you needed it theoretically for the confidence intervals. So that's not actually what's done. Right. So we don't include, so that's one thing. We don't include any covariates because we want to do the stability, because we want to avoid the tuning thing because that's not stable in the pipelines. And if it were stable, I'm not going to do random forest anyways. I'm going to do something else. Right. And the last thing is you want leave one out OLS at the last step to get because regularization is going to get you on the long scale. So if you did all that, and there's an algorithmic form, it's very simple. Then it's just what I said. In this case, it fixes the bias. Now, this case, of course, trivial for it, as we'll see from our theory, our very simple theory, that, as I told you, the true here is a linear model. There's 10 covariates, only 3 matter. Any subsampling is going to induce a bias, and we can theoretically show that a linear adjustment at the end is going to get you back. Is going to correct the bias thing. So that's the thing, that's the idea, that's how we got into this. And no, one of the ways we got into this problem was ignoring Leo, who actually did applications that, oh yeah, his forests were biased. We also moved away from out-of-bag to this honesty thing that seemed clever, and it is clever, but actually got us into a bigger problem than just undoing it. So part of the joke about this is on 2 different layers, undoing 20 years statistical development back to Leo. And you're like, I don't know, I'll leave. There might have been a gain if I had stopped reading. Anyways, so here these are empirical CATE simulations. These simulations are not ours. They're from this wonderful paper by Liwa and Manuel. And in there, they report that if you do conformal interval, and it's of course very good properties if you use any of these standard learners, if empirical coverage is 70 to 90%, so it's not very good. We don't change the simulations at all. We just debias it in this very simple way. And what we'll see is, like in the high dimensional cases where the problem arose, that coverage is now much closer to nominal. Obviously, it's not perfect. You can see it's undercovering a tiny bit here and here. Conformal, of course, provides guaranteed coverage, and it's very good, but it does fix this quite large bias. Well, I'll give you some of our own simulations where it doesn't look as good. We created some adversarial simulations in a second. So the thing is, the intervals are much, much smaller. So the coverage is not quite as good as conformal, although it's very good. The intervals are much, much smaller. The conformal intervals are so large that, as I said, in data problems, you're going to have an average Schumann effect of t-stat of 3, and conformal thinks that nothing is significant and I know what users are going to do. They're just going to like go do some random thing now. They're not going to stop at this point. And you'd like them to think, well, maybe on the Edge-Human effect, I'm trying to estimate a more complicated model. Maybe I should just revert back to the mean estimate. You get a selective inference problem, but that's not what's going to happen. We'd like it to happen, but I'm here to tell you that's not what 98% of users are going to do. Right? All right. So that wasn't the main motivation. One more simulation. There's an adversarial simulation. It's the same simulation from this paper with Peter. It comes from the science paper article that two of my grad students wrote, David Brockman and Josh Kalla, in which they showed a policy and an intervention that would reduce transphobia. It got a lot of media attention, not only because it was about transphobia, but also because there was a pre-existing article on the topic that turned to be fraudulent, that David and Josh found through data forensic was utterly fraudulent. The data was completely made up. It's a pretty extreme case of being fraudulent. The data was made up, but the intervention itself, which was done by a third party, was actually good. So they thought they needed to do it. Now, part of what happened is they used an experimental design that David and Josh came up with, which was to have a lot of power. And the way that experimental design gets a lot of power is it collects covariates that are very powerful predictors of outcomes, right? So what ends up happening is, although in their experiment, the t-statistic, the average mean effect is well over 3, the treatment is less correlated with your outcomes than your baseline covariates that we gathered. We did that because that's going to give you lots of power when you adjust for it. And we adjust for it in experimental design. So the R squared of if I regress Y on your baseline covariates is like 0.8. So that's like having 5 times the sample if you just do the algebra for that. So if you throw that though with the S-learner, the S-learner ends up being horribly biased, because whether you do lasso or you do ridge or you do random forest, because the regularization is making you regularize the treatment effect very seriously. So the simulations based on that real data. This is the signal to noise ratio set to what it was in the data. This is with higher, this is for lower. And you could see the we picked the learner which is particularly bad. The coverage in this data simulation is very bad. It's way worse than in Liwa and Manuel's simulations. It's like less than 20% when you ask for 95% interval. If you do the bias correction, it's still not great. It's because it's still not overcoming the central problem that the S-learner is not targeting the causal effect. So there's probably a different learner you should use. The one that Peter and I and our co-authors proposed does better here, but it still it's moving in the right direction in a very large sense. As an applied person, I'll tell you, if I could get 75% coverage of when I ask for 95 for a problem I actually care about, this is a massive win. Let me put it this way. If we go, hey, on the mRNA vaccine, should we have a 4th booster or 5th booster? We have nowhere near 75% coverage of our predictions. So all of the game is how biased are our estimates, because they're very biased. So from a statistical sense, this is bad. From a policy sense, amen. And most problems I work on, I'd be happy to take this, and I don't get this because I'm worried about the bias side. So the applied example here is this Get Out the Vote campaign. We've done it on lots of different Get Out the Vote campaigns, done it on medical things, we've done it on some finance examples. This one is that, all right, so we did this in this paper. I've gotten a lot of feedback on this paper, and people have literally found out, applied people found out this bias. So in the United States, whether you vote or not is a matter of public record. For whom you vote is private, but whether you vote or not is public record. That kind of creeps people out. So a very effective treatment is this very simple mailer in which you send out a mailer and they say, hey, what if your neighbors knew whether you voted or not? And you tell people the voting history of themselves and their neighbors, and they tell them that after the election, you're going to mail out an updated version of this. And then it gets people to turn out to vote. It causes an increase of voting about, say, 7%. It kind of varies on, is it on year, off year exactly, but that's a massive treatment effect for a postcard, which is very cheap. Now, some people do seem to have a negative treatment effect, and other people have no effect at all. So there is a backlash. So you do want to target it, right? So in our paper, what we showed was, and this is just from our paper, that there's a histogram of the conditional average treatment effect across individuals, and it's a large scale study. This in our paper, this was 120,000 controls, about 30,000 treated. This has been replicated in studies with millions of observations. Well, you see the same thing. There's a large treatment effect. Yes, the average treatment effect is quite large. 1 is coded whether you vote, 0 coded if you're not. And the shaded areas are confidence intervals for whether it's significant and what proportion of those bins significantly departs from 0. You can see that, yes, there's a large average treatment effect, but there is a subgroup for which there's actually evidence and you want to target that. It varies a lot by age or your prior probability of voting. This is the x-axis here is your prior probability of voting. The treatment effect is pretty intuitive, is quite large if you have some history of voting, but you don't always vote. If you always vote, it's much less. If you never vote, it's much less. Here's the box plots, I think, are the easiest way to see that. If you don't have a voting history at all, it might have a 0 treatment effect, which I think makes sense. If you never vote, it's kind of hard to get you to vote. Right. So in this case, so you can do it by simulation and then on the actual data. So we take the same simulations from our previous paper and data inspired. So you're like, just assume that the data and the response model is true, that the debiased estimates then give you an average treatment effect estimate of 2%, where the truth is 1.8%. And if you don't debias them, like we didn't in that paper, and then people, when they implemented this in their pipelines, didn't debias it, you get a pretty biased estimate of 1%. So you're pretty far off. And so you're off on the mean, and you're especially harming predictions away from the mean. And also you gain mean squared error, not on your prediction of y, but on your prediction of the CATE itself. Well, obviously, you're not getting mean squared error in the prediction for y because the base learner force did that mean variance trade-off correctly as it was designed to do. So on the policy side, if you go through this and you're like, okay, votes are going to be worth different amounts to different actors, different campaigns, and in different settings. But if you say that, okay, votes are worth, say, $31, that corresponds to a conditional average treatment effect of 2%. So I'm going to increase probability of voting by 2%. The debiased estimates imply that, well, I should target almost half of my potential voters. The debiased thing was only 32%, and the true percent is in the simulation, since we know it's true, is 45%. If the vote is worth much less, and this is what it's kind of like for mayoral elections and whatnot, then you need a conditional average treatment effect of 5%. And now it says you should target about 7% of potential voters rather than 3%. The truth is 8.4. And then the debiased predictions also are fixing this negative thing at the bottom end. The debiased things think that 12% of potential voters have a negative effect from this mailer. The debiased thing had almost 30%, and the true percentage is like 18 in the simulation. And the same thing parallels on real data. We have medical examples and others. All right, I'm going the wrong way. I keep doing that. All right, some very simple theory. So the very simple theory is, all right, much like for random neural nets, for random forests, people worked up simple linear models as a way to understand random forest, because doing theory in random forest is very hard. So imagine the data is generated by a linear model, IID, and then here's the key thing. I'm going to bag it, and the key thing is I'm going to go up and estimate those coefficients. I'm going to subset a random subset of the linear features in each bag. So I'm going to bag a linear model. I'm going to subset covariates in each bag, and then I'm going to average over bags. Right? So when the size of the subset is smaller than the original parameters, and I get enough bags, this estimator then is going to give you a scaled version of the OLS estimators and then estimates, and then probably pretty obviously, given the setup, a single linear step bias correction can debias the pointwise predictions of the estimator. Right? So you assume that this is the low dimensional case. We should probably work out the high dimensional case. So n is greater than d. D is the number of features here. You assume the data is mean deviated. We subset less than the number of covariates, and then what you're going to get is, as you start bagging, your actual less coefficients are a scaled version of the true coefficients. Here. And again, given the setup, it's pretty obvious, I think, then, oh, well, if I do a one-step linear fix, which is I don't I don't use the covariates. I just go y on y hat. I get a scale parameter. If I go I get a scale mean and variance. I go do that. I'm gonna be then fine, right? So what you can learn from the very simple theoretical example is that while consistency in the pointwise bias gives us power to estimate and correct the bias, this is not always possible because you're going to have small data and heterogeneous pointwise bias, and that's going to make it kind of unfeasible. So I'm running out of time. I'm going to say that, okay, so bias prediction can help fix these random forces. I've noticed the same thing with neural nets. I've noticed the same thing with XGBoost, although not as drastic. Partly the key things is for things like XGBoost and neural nets, they're tuned for the prediction problem, which makes a certain mean variance, a bias variance trade-off, not the policy bias variance trade-off that you want to make. And although it's not the main motivation, I think it's like helpful for confidence intervals. Before this work, we kept thinking, well, you get estimators whose bias is going down root n. You want confidence intervals at root n. Of course, the bias is going to be really bad, and you can't make progress because you're not getting the parametric rate. Turned out, I don't think that's what's going on. I'm sure that's what's going on in part 2, but you have a simpler problem. Thank my co-authors, and we have software. We have lots of software. Go check the software, and I shall stop.
So thank you, Jess, for wonderful presentation. It was so wonderful. Your alarm forgot to turn on. So it's great. Thank to Peter too. I think it's a special treatment for a special day. So alarm didn't test today. So let me see if there are any questions.
But you need to give Peter the microphone,
yeah,
because
sure.
Jess will not hear otherwise.
Okay.
Jess, I was just wondering, with these very complicated situations, can you sort of measure the effect on your bias of factors, confounding factors, which you don't know and don't observe, or you have? In other words, can you get some idea of what magnitude of perturbation could really ruin these predictions?
Yeah, that's a great point. It's now you can't get something for nothing, as our friend David Friedman once said. To pull a rabbit out of a hat, you got to put the rabbit in the hat first. So in this case, yes, but now you have to bring some structural knowledge. Like in these policy evaluation cases are complicated. The upside is people have structural knowledge because they keep doing it, or at least they claim to. At least you can have a conversation about it. And now you're like, yes, okay, so these are the perturbations that are important. This is, I think, the size of those perturbations. And that's a long process, right? It's sort of like, it's I was talking to Ben the other day. It's like, hey man, for statistics, we've been doing it for over 100 years. We've agreed on 2 numbers, your estimate and your variance. Surely we should have another number that's something about stability, a perturbation, like you're saying, like what's the bias that could be threat? What's the third number? And we haven't agreed on a third number. And I think part of why we haven't agreed on a third number is it's very contingent on your problem at hand. Like maybe for your problem, your p-value is not relevant, as I'm arguing it often isn't, but at least everyone knows crank the machine, out comes this p-value, which is a kind of perturbation, right? It's the perturbation over the randomization distribution, in the case for a randomized control trial, or the sampling distribution kind of sampling. So in practice, I do those perturbations a lot. Those depend crucially on the application and then how bad we think the bias is. I mean, an example I'll give, which is like, hey man, if you're all going to retire, you all have some investments. If you think the equity markets the next 5 years have done what they've done in the last 5 years, it's probably unwise because we haven't had inflation since the 1970s, and we now do. Right, so every macroeconomist in the room can think this through, and we know, like when you look at the data, how the data is biased for the near future, and we can have a conversation. Now, if you're not with a room full of macroeconomists, that's not an easy conversation now. Like all the macroeconomists will not, they'll still disagree about the magnitude, when it will revert, when it will not revert. But that's like that covariate shift that's occurred can be reasoned through. So if anyone in that case is going to have some data, one's going to then say, all right, how do we think that through? And of course, people disagree on that. That's kind of what happened between the FDA and the Israelis. Was you're getting old people that were getting the next vax. the people in the FD were like, well, what about the bias? And then the Israeli view, which I agreed with, was like, yes, these are old sick people, so the bias goes the wrong way. Who's getting the booster are people at risk, not the people not at risk. So you'd think the bias has the different sign, and I go, well, that makes sense to me. And some people, the FD goes, oh no, it's biased, and I don't want to give you the sign. And I'm like, well, you have a decision to make, you better sign this. And I think the sign direction the Israeli epidemiologists were making was the correct one. But then you get this, it's not unresolvable, but I think we eventually made the right decision. Partly because we did that perturbation you're asking. Well, I was like, okay, there's a thing, we can't observe it. Which direction do we think is the sign behaviorally? And it would be pretty unreasonable to think it's the other way, that old people are getting it less and they were at less risk. That makes no sense.
So let me see. Yeah. So, oh, sorry.
Thank you very much for the excellent talk. I felt I learned a lot. I have two questions. The first is about your theory about what random forest does. I thought I want to reconcile this with something else I've read. There was a paper from people at Rice University saying that when you go through the bagging, you get something like looks like a ridge estimator. And it's by Ginevra Allen and colleagues, which is not what you get. You get a rescaled version of OLS. You don't get the ridge estimator. So maybe can you please clarify for me the difference between the two? Why is it that you're not getting the ridge and you're getting a rescaled OLS?
Yeah, so it is here. Let me see if I have the slides. I can send you notes after on it. Our results are consistent with theirs, and this other channel R thing here. Let me see if I'm not sure I have these notes here. There is I don't have it. I don't have it here. But I know those results. Our results are not inconsistent with them, but I don't have the results here to give you a clear answer. I think, but did they have like the P less than N case?
Yeah, I think so.
Yeah, I can't off the top of my head, but I've seen those. I have those results. I'll send you the notes.
Thank you.
But I don't know off the top of my head.
And my second question is more of an observation, is about, of course, the comparison with conformal prediction. So the goals are very different, I think.
Oh wait, I do know the results. Sorry. I'll go back to the. May I answer the previous question? Yes. So the theory I gave here was under the linear model, not OLS. This is OLS. I'm subsetting OLS. I'm bagging OLS. I'm subsetting the OLS. And then you get the bag result.
I think this is the same setting as what they have, if I remember correctly.
All right, we should talk about it.
Okay. The second is about the conformal prediction. It's more like a clarification. Conformal is really trying to predict the individual treatment effect itself, not its mean. And so the fact that conformal predictive intervals are wider is a necessity, because you're trying to predict a random variable, not a parameter. So if I can speak that way. And so the fact that they're wider, and I think there's room for both, right? There are cases where you really want to know the mean, and cases where you might actually care about the variability around the mean, because, and I think Judea Pearl argues about this a whole lot, which is that, if the mean is positive, but for a lot of people, they actually have negative effects, that you would want to know about this. And so it's just perhaps a clarification that because one method is designed to predict an outcome, a random outcome, then by necessity, the prediction interval will typically be much wider.
I agree, although in the simulations I showed on the comparing it to conformal, we're doing it on the individual effect. You're estimating the CATE, you're using the CATE to estimate the individual effect, and you're comparing it on the individual effect. And the coverage properties of it are off the individual effect.
On right. Y1 minus Y0?
Yeah. Under same simulation as yours, just the same, everything's the same. Right.
So maybe we can talk about this offline, because there are many, the conformal is not really a method. It's like what base learner you're using and things like that. But maybe I'll follow up.
Yeah.
Thank you.
Yeah.
Christian.
Okay, I have a, well, maybe related question to that. So there seem to be some of my social science friends tell me that if you do these shaming experiments, there's really a large difference on whether you are more Democrat or more Republican leaning. So it seems to work much better on Democrats, whereas the Republican leaning will say, screw you, I don't want to be shamed into anything. I do what I want to do. And now, would that have an effect on, so when you debias, could it be that in this example, you would debias the mean, but you actually make the effect of these two heterogeneous groups worse?
Yeah, that's a great question. So it could always be that you do make it worse. In the shaming thing for voting, there's not a partisan effect because the norm of voting is not partisan. The shaming effects show up in pretty partisan cases. Like, for example, a famous one is in Los Angeles. The power company was trying to shame people to conserve energy. And it had a differential effect among Republicans and Democrats. Republicans started consuming more energy because unfortunately, when it comes to energy and environmental issues, it's become, the norm is now, it's become partisanly aligned. The voting norm does not itself have a partisan divide, so we don't see it in this case. But in those cases where we do see it, I am certain there will be cases that if you debias it, it's gonna like induce a problem, right? I haven't seen it, but doesn't mean it won't occur. I'm sure it will occur. Bad things will always occur in data. And it's certainly true that there are shaming in general, if you use norms that are have a partisan cleavage on them, will play out in partisanly divided ways.
Would you rather not debias if you know that there's a partisan effect?
Well, if the bias step is causing it, like, I don't know if it is. I'm willing to believe, like, anything someone says, I have an X machine, can it cause a problem? X will always cause a problem in some settings. I don't know whether the debiasing will cause an issue here in that case. I'm just saying it might, I don't know. What I am observing is what the debias is partly doing is mostly happening in the tails, is the force is regularizing the tails quite a lot, right? So when the forest tails come in, so it's actually you can see the slides that I had is that, and in the nonlinear versions of it, that's where it's helping, not in the mean so much. So the debiasing is a bigger issue on the tails. So it's like, hey, if it's tail behavior, it's gonna have the debiasing is a bigger deal on the tails. Right, you should think about what a forest does at the end, right? It's like, I'm in a neighborhood, I'm using a mean estimator, I'm going to get neighborhoods in the mean at the end. I'm doing a shrinkage towards the mean of the last node. So the tail, the debiasing steps actually help the tails more than anything else. So if the bias is happening in the tails, then I think the debiasing may help. But I imagine, I'm sure there's cases where it will hurt.
Yeah. So yeah, I mean, we are running a bit late. Let's thanks to Jas again, and this concludes the morning session. So, is that you have an announcement or just come back?
Yeah, we'll come back at 1:40.
Come back at 1:40, right? Actually, yes.